Hi, I'm Florian, and I'm excited to present our work on uncertainty-aware vision-based metric cross-view geolocalization. In our work, we address the task of matching the camera images of a ground vehicle against geo-registered aerial images to predict the geo-pose of the vehicle. We consider a search region of several tens of meters around a prior pose estimate, for example from a consumer-grade GPS sensor. Our method then predicts a probability distribution over the vehicle's position and orientation. Our main contributions are as follows. We propose a novel end-to-end trainable model for this task that outperforms related works by a large margin, even in a zero-shot setting. We gather a large amount of diverse data from multiple public datasets and improve the inaccurate ground truth poses via a pseudo-label approach. We publish these labels as well as our code online. Let's first look at the model we designed for this task. On the right, you can see a flowchart of the model with the input images at the top and the output probabilities at the bottom. We first extract pixel-wise features from all of the input images using a simple encoder-decoder network based on the Confinex architecture. We use one such model for the aerial image and a second model with shared weights for all of the ground images. We then project the features extracted from the camera views into a bird's eye view. This is called the PV to BEV task. We choose a transformer architecture for this purpose that builds the bird's eye view map by cross-attending to the perspective view features. The bird's eye view map is iteratively refined by applying cross-attention as well as self-attention in the bird's eye view. Finally, we match these bird's eye view features with the features extracted from the aerial image to find the vehicle's pose. That is, for each pose hypothesis in the search region, we transform the bird's eye view map into the coordinate system of the aerial image and define the likelihood of this hypothesis as the matching score between the two maps. Multiple hypotheses can then be evaluated jointly by using a cross-correlation operation, which can be sped up even further by computing it using fast Fourier transforms. This is what enables good performance even when exhaustively evaluating all of the poses in the search region. This model is end-to-end differentiable and therefore requires only the ground truth poses of the vehicle as supervision. As the loss function, we simply compute the cross-entropy between the predicted probabilities and the ground truth. Next, let's get to the data that we trained and evaluated our model on. Since there are no large and diverse cross-view matching datasets with accurate ground truth poses available at the time of our publication, we instead combine multiple datasets from the autonomous driving sector with aerial images from providers like Google Maps and Bing Maps. This results in a total of 2.5 million data samples, where each sample consists of the aerial and ground input images, the camera parameters, and the ground truth pose. Since these samples are distributed unevenly over the locations in the US and Germany, we also measure the total aerial coverage by dividing the data into cells of size 100 times 100 meters and counting the number of cells that contain at least one such data sample. This results in a total of 13,000 cells. Similar to previous works, we find that the datasets contain inaccurate ground truth poses with up to several meters of error, which might, for example, be due to low-quality GPS measurements or bad geo-registration of the aerial images. We therefore design a pseudo-label approach to improve the ground truth of these datasets by also including the LiDAR scans in the PV to BEV step of the model. On the left, you can see some qualitative examples of the improved labels, where the LiDAR scan is projected onto the aerial image. We further design an automated data pruning approach that can be used to remove invalid samples from the datasets. For example, where the vehicle is traveling through a tunnel or where the aerial and ground images are out of date. On the right, you can see two trajectories where our method detects that the vehicle is traveling through a tunnel. Here are the results of our method on the Ford AV dataset, with a search region of 28 meters radius and 20 degrees orientation uncertainty. The table shows the recall, that is, the percentage of predictions within 1, 3, and 5 meters of the ground truth location. We separately evaluate longitudinal and lateral recall, and find that the former is generally more difficult to predict than the latter. When trained in the same setting as prior works, we improve the state-of-the-art by a large margin. In this setting, the model uses only the single front camera of the vehicle and is trained and tested on the same aerial images and on camera images captured using the same vehicle. We additionally show results in a cross area and cross vehicle setting. Even though this represents a more challenging setting, since the model has to generalize to unseen areas and to unseen camera setups, our model still outperforms previous works which were trained on same area and same vehicle data. Lastly, we show that using all of the available cameras, rather than only the front camera, further boosts performance by a significant margin. Here are some qualitative results on the Ford AV dataset, using the model trained in a zero-shot setting. The first two rows show the front and back camera of the vehicle at 4 different timestamps. The last row shows a corresponding aerial image with a search region and predicted probabilities. In most cases, there is enough discriminative information in the environment to uniquely determine the location of the vehicle. The third column shows a more difficult example where there is high longitudinal location uncertainty and highlights why the lateral location is generally easier to predict than the longitudinal location. This is a demonstration of how our method can be used to predict a vehicle's trajectory over time. We use a simple Kalman tracker that integrates both inertial measurements as well as the uncertainty-aware predictions of our model. The video shows a scene from the Ford AV dataset with the vehicle's front camera on the right and an aerial image centered on the predicted vehicle location on the left. Here we also show the projected LiDAR scans to allow evaluating the registration qualitatively. The LiDAR scans are only shown for visualization and not used by the model. To summarize our work, we introduce a novel model for the vision-based metric cross-view geolocalization task that achieves state-of-the-art performance even when applied in a zero-shot setting. We gather a large amount of diverse data from multiple public datasets and improve the inaccurate ground truth poses via a pseudo-label approach. We make our code as well as the improved ground truth publicly available. Thanks for listening, and for more information, please check out our paper and project website.